All right, everyone. How are we doing today? Doing okay? All right. So uh, today we are going to continue on in chapter 14 here. And the idea is that we need to take our new knowledge of partial derivatives and use that to kind of continue on in discussing what it means to deal with derivatives in higher dimensional situations. Okay. So last time we talked about functions that had a sum form like this. It can be something weird, right? Okay. And the idea was that we discussed the idea of differentiating this expression with respect to one of the independent variables. So we can go through and compute this derivative, partial derivative to be more specific. And we can also compute the partial derivative with respect to y. Okay. And we get these expressions here. Now, this part, fairly straightforward. Okay, we basically just talked about the calculus and the algebra involved in doing these computations. Okay, um, where we have tried to add some information is to figure out exactly what it is these things mean. Forgot to get that connected before launching the stream. Okay. So let's hold on. Sorry. I'm trying to let it. It's not letting me do the 3D calculator for some reason. There we go. Goodness. All right. Sorry about that. So let's type in our formula here. To get an idea of what this surface looks like. And it's going to be crazy because I was just typing random weird stuff. Okay. And so we see that we have the surface here, and rotating it's going to be kind of a slow process because it's a complicated thing to compute. All right. But we see some interesting stuff going on here. Okay. It's kind of subtle in the image for the picture, but one of the things that they do show, as you can see down here, is the um, the curve if we project to one of our planes. Okay, so this is what's going on in the XZ plane, or sorry, the YZ plane, where x is equal to 0. Okay, and that's a reasonable guess because we have what's obviously cosine, right? And that wouldn't work in based on our formula if we were looking at the other curve in the x direction, which If I turn the graph slightly here, it's a little harder to see, but this curve here is shown. Okay. Now, that actually relates to what we would think about if we were looking at some partial derivatives. Okay. So one of the things that we can do is we can decide that we want to look at some particular plane. Okay, we can say y equals 1. And what that does is it gives us a plane that cuts through our surface here. Okay. And again, the picture is quite busy because of how complicated the surface that we originally graphed was, but we have the ability to take a look at this. All right. And we can change this plane to some other value and see what it is going on here. Okay. Now, will it let me do this? And is that even helpful? No, because it just graphs the function in 2D. I'd have to rotate it. Okay. Sorry. Not as helpful as I would have liked. Okay. But so we can turn this off, and then we can also take a look at some other thing, which would be, say, x equals 1. All right. And that gives us a different plane that goes through and cuts through our surface, and we can see, again, very lightly where that intersection of the surface and the plane happens. Okay. You can also perhaps change this to 0 and get a more pronounced showing of, yes, indeed, this line here occurs when x is equal to 0. If we want to, for a particular thing, you can change the color to something more pronounced. So it's not like blue and gray and a bunch of similar colors on top of each other. I've not really found anything that's helpful. Anyway, I just made it worse. Why is that pink so gray? Okay, that's better. Sorry. All right. So the reason I bring this up is because this is the kind of thing that we're thinking about when we talk about partial derivatives. All right. We, of course, know that when we compute partial derivatives for a function, it makes what we're really doing is writing formulas like this as a shorthand for the formula of taking the derivative at a point. Going all the way back to our understanding of Calculus 1, you don't define this first, right? What you define first is this: the notion of the slope of a tangent line at a particular point, okay? And then from there, it is expanded to mean the class of values that have meaning where the function is differentiable, right? We talk about the property of differentiability and then work from there and then build up to this more generic thing that's the derivative formula for the function. All right. I want you to think about partial derivatives in the same way. Okay. We have this tendency to skip to this just due to this is what we're going to be writing down in practice most of the time. You just write down the partial derivative formulas and then work with those. But what this really means is I can plug in a point AB anywhere where my surface is differentiable, anywhere where it's smooth enough, it doesn't have corners or cusps or discontinuities or any nonsense like that, okay? And get the values of the slopes of the tangent lines at that point along one of those cutting planes, okay? So we have our little coordinate system here. We're going to have a poorly drawn surface. And the idea is that we have some cutting plane down here that cuts through the surface and gives me some curve, okay? And then if I'm interested in what's going on at a particular point, then I can think about the tangent line there, okay? And if I have this picture, repeated, and I have some other cutting plane that looks like this. I'm interested in the same point, right? But it's going to give me a different path along the surface. And I'm going to have a different tangent line. Okay. Now, there's one thing I have to change about this. These pictures are in the wrong place, right? This is the picture for Y. Okay. So let me fix that. All right. So that kind of stuff's going on. So that's from a theory standpoint, what partial derivatives mean. Okay. And I went through all this because it connects to what we're going to be talking about today, which is concerned with the idea of a tangent plane. Okay. All right. So all of this is about, oops, let's turn off the ruler. Partial derivatives. And now we want to talk about tangent planes. Okay, so starting with this picture that we already have here, there was a point that I had chosen that kind of sat down next to this hill shape that I have sketched out here. And so we have some point that's kind of sitting down here. Now, what I have, if I look at the pictures above, are two lines, right? These lines have a slope, okay, and they pass through a point, all right? And if I have two lines that both pass through the same point, what do those lines define? I have non-intersecting parallel lines, or sorry, I have intersecting non-collinear lines, right? So you are correct. They form a plane. All right. It's sufficient information to give me a plane because what I can do is I can have the intersection point between these two lines, right? And then I choose any other one other point on both lines. That gives me 3 points. 3 points to find a plane, and so we go. All right. Now this is important to us because this plane that is defined, and I'm using the same color that I used for the tangent lines, because since I used the tangent line directions to define where this plane sits, this plane is tangent to my surface, right? In both the x direction and the y direction. Now, it is very difficult for me to draw a sketch that really shows what's going on here, okay? But what I want you to imagine, and if you have stuff sitting on the desk that you're currently sitting at, or just imagine this in your mind's eye, okay? Imagine you have, say, a basketball, right? Okay, or some other sort of sphere. What you can do is you can grab a piece of paper or a note card or something, and you can lay that note card on the surface of the sphere at a point, okay? This is what we mean by tangent plane, all right? And obviously that plane extends infinitely in every direction, as planes do, okay? But what's important about this is that I have a sense of direction of what's going on in the x direction and the y direction for that plane, okay? The directions of the plane and its orientation are related to the partial derivative computations we just did, okay? And without getting into many of the details right now, this is the idea that is the natural extension of tangent lines and derivatives that you're used to for high dimensional functions, okay? Since we have two independent variables for the problems that we've been discussing up to this point, we require a derivative object that has a geometry that allows for motion in 2 dimensions. So we end up with a tangent plane as opposed to a tangent line. And we've done enough discussion up to this point in this class to where if we're thinking about traveling along the line, we know that that is a one-dimensional object, right? It permits movement in only one direction, like a space curve only permits movement along the curve in one direction, okay? We tend to, of course, graph them in higher dimensional context, and that object makes sense, but from the perspective of topology, which is how we think about it, it's a 1D object. There's one allowable dimension of travel. Okay, tangent planes have 2. And most surfaces, of course, that we've discussed have 2 dimensions on them. Because if we're traveling on the surface, there's only 2 ways that you can go. All right. Now, to define planes, we, of course, go back to some of our formulas from earlier chapters. And we have the standard form here, and where the right-hand side is equal to 0. We can do some extra computations with the goal of isolating z, because for these exercises, we are, of course, thinking about z as being a function of x and y. So we want to recast things using this relationship. Okay? Now, yes, I divided by it. That's why capital A and capital B changed to lowercase a and lowercase b. Yeah, I wanted to get z minus z naught by itself, and uh, there's a reason of convenience why we divided by the capital C. No worries. I wrote something down without at least describing what I was doing. Okay. Now, what we gain from this is that in order to know the equation of the plane, we need 2 pieces of information, okay? Well, 3. We need to know a point on the plane, and we also need to know the values of these constants a and b, okay? Now, fortunately for us, there is a small amount of justice. And it turns out that these values are like they are in the case for tangent lines, the value of the derivative at the point that we want to find the tangent plane. Okay, much like it would have been f prime of x naught if we were talking about a tangent line. Okay, so the division by c basically made the equation look like y equals mx plus b. Okay, the plane version of that version of the equation. All right, so this is our tangent plane equation. Thank goodness it's easy to remember, right? It's just a plain version of the point slope formula. Okay, that's another way to think about it. Okay, all right. So let us do an example here. We want to find the plane tangent to z equals 2x squared plus y squared at 113. Okay. So we start off with our formula for our surface. And we need to compute the relevant partial derivatives. we start by finding the partial derivative formulas, and then we'll plug in our values. So if I take the derivative of this expression with respect to x, I'm just going to get 4 times x, because the derivative of y squared is 0. And if I take the derivative with respect to y, I'm just going to get 2 times y. Okay. Next up, we plug in the x and y values for the point that we're interested in. 4 times 1 is 4. And 2 times 1 is 2. Okay. And of course, the 1 and 1 just come from the point where I want to compute the derivative. Are there questions? Is there something that's hard to read? Okay. All right, so we have our values here. Now what we can do is we recall our previous formula. And having written this down, we can plug everything in here. And rearrange it if we would like. Okay, so we get -4 minus 2 plus 3 gives us -3. Okay. So this should be our tangent plane at the relevant point. And let's jump back over here to this. On keyboard shortcut, okay. And then type in our expression to see if everything worked the way that it was supposed to. All right, so we're gonna have two x squared. So I clicked off the page. Sorry, sometimes these websites run really slow because I'm streaming at the same time. I clicked something. I got the sense it would be faster to just start over. All right. Okay, 2x squared plus y squared. All right, and what we have here is an ellipsoid. Okay, and now what we want to do is use our formula for our our value here in order to show that this is a tangent plane, and I will zoom in and rotate here so that we can see that that's what's going on. Okay, now the image here isn't perfect, but what we can see if we try to pay careful attention to the axes is that up here, this is 3, okay, and this is where our tangent plane touches in the Z area. 1 here is pretty easy to see, and then 1 down here is the value for, I don't ever remember if red and green is X and Y, but we have, it's a tangent plane, okay? See that that's where it intersects. What happens if I try to just plot a point? Yeah, okay. I plotted a point here. Okay, we can see that that's where the intersection occurs. Right? So it works the way that it's supposed to, which is nice to see. Okay. And if you want to verify what you're doing makes sense, okay, to make sure that, for instance, you have correctly computed a tangent plane, one of the things that you can do while you're getting used to this is use this website, okay, as a way to just kind of quickly verify things. It also gives you a little bit of experience in seeing what these surfaces look like so that you have that visual check available to you, okay? I know it seems like moving the pictures around and everything runs really, really slowly, okay? That's because I'm doing terrible things to my laptop being here in class, okay? I'm live streaming over Wi-Fi because I don't have a wire connection here, and it would be fairly slow anyway. So doing the best we can here. All right. And my projector just decided to mess up. Okay, hold on. Let's figure this out. All right, hold on. Technology problems. The rest of the section here goes through and shows the mechanics of kind of rebuilding some of the basic ideas that we had from one-dimensional derivatives, okay? In particular, what it looks like is taking this formula for the tangent plane and then reminding you that differentials work for tangent planes the same way that they would work for one-dimensional functions, right? In the 1D case, what we had was some curve, and we could look at the tangent line to that curve at a point, all right? And by looking at the tangent line to the curve, we could imagine the dy and the dx, right? So we would have dy here and dx, okay? It works basically the same way for planes, okay? If we have a situation of the tangent plane to some surface that is tangent at a point, okay, I can imagine moving in this direction or this direction, like we talked about earlier, right? Okay, and it's harder for me to draw the little triangle in a way that's easy to see, but you can imagine the change in z with respect to x and the change in y or the change in z with respect to y, excuse me, okay, and have that be a way to approximate what the function does close to where the tangent plane touches our surface, okay? This process is one of the most important processes from the purposes of using partial derivatives in order to analyze functions, right? This is known as a linearization. Okay? So if I have a surface and that surface is difficult to work with for whatever reason, or I have limited information about that surface, what I can do is I can employ the derivative, generate that tangent plane, and then use that tangent plane as a way to local to where the plane is tangent, approximate the function. Okay? And this is a very common process in applications. Okay? We have some touch point for our information, okay? Some data point that we have measured about our object, and we know in a very short range around that how that data may be changing, okay? So for instance, if we know the gas price today and we know the gas price has gone up a couple of cents every week for the past 3 weeks, we can use that as a way to project what the gas price is going to do in the short term. Okay, would be one way that we could do that. Or another way that we can think about it is we're selling milk, okay, and we know that the last time we sold milk at a particular price point that it sold this much, right? We also know how much milk we have in our warehouses, all right? And what we don't want to do is lower the price to the point to where we're going to sell all the milk in the warehouse. That's bad, okay? So we can try to use these approximations to estimate what is a reasonable change to the price that will not cause us to sell all the way through our inventory. Or we can think about the problem from the opposite sense of we have a warehouse full of milk. Milk goes bad, right? So we need to sell through our entire warehouse full of milk, okay? And where can we do the calculus necessary in order to set the price point to maximize profitability while also doing the absolute best that we can to make sure that we don't have waste, because those waste cuts into our profit. Things like that, okay? These are all calculus problems, quite literally. And as we cover a couple more sections here by next week, we'll be able to do the kind of calculus that would be necessary to be able to discuss some of these issues. Okay, we're going to start off with some more geometry focused stuff. Like I had mentioned last time, the joke about the soup tin really being most efficiently made to make it look like a cat tin, but we can't do that because people won't buy it. But those kinds of things. Okay, so I don't want to jump into an example here because I don't know when our tech people are going to show up, and we've only got a couple minutes left anyway. So what I'm going to do is encourage everyone to look at the textbook for this section. The main thing that I want you to read through and experience is the way that the textbook uses the notation, just so that you have more exposure to different ways of writing down these kinds of things, okay? I don't want to just write a bunch of symbols here really quickly before we leave because it won't have the accompanying explanation, and that's not helpful to you all, okay? But you do need to see the more of the partial y, partial x, or partial z, partial y sort of stuff, just to get an idea of what things are looking like. And then also there are a couple of useful examples where they take partial derivatives as expressions that look like this. Okay, for instance, this is the volume of a cone. Okay. And so this would be a thing that you could take the partial derivative of. For instance, you might be interested in how the volume changes as the radius changes, okay? Or how the volume changes as the height changes, okay? And obviously, since this is a multivariate function, it's going to depend on potentially what the other variable is doing as well, right? But you want to know how those scaling factors work. And this would be another example of, say, we want the best ice cream cone, okay? And there's actually ice cream down here. All right. How do we What do we do in order to make the ice cream cone hold more ice cream? Okay. Huh? Well, we just pile it higher, right? Anyway, not so much. I think it's pretty clear from the equation that the answer is to make the ice cream cone look like this. But that makes the ice cream cone harder to hold, so we can't do it that way. But there are situations, of course, where we actually do get to use the mathematically most efficient answer. And this is how we would go about finding it. Okay? So let's call it for today. And our tech people haven't showed up yet. I'll stick around for a couple extra minutes to see if I can get this business sorted out so we don't have to keep fighting with the projector here. All right. Take care, everybody. And I will see you next time.